These are the Unit 6A Module 1 notes on systems of equations. Today we're going to talk about what a system of equations is, and we're also going to look at how you can solve a system of equations using a graph. First of all, what is a system of equations? Well, similar to like a flock of geese, a herd of deer, murder of crows, intrusion of cockroaches. A system of equations is just a group of equations, but this is a special group of equations that has the same solutions. So if they have the same solutions, we call it a system of equations. Now, what exactly is a solution to a system of equations? It's a set of values that makes both of the equations or all of the equations true. So we're going to look for possible solutions to these different sets of equations that we call systems. First question is 4, 5 a solution of this system? To figure out if it's a solution, we're going to substitute 4 for x and 5 for y into both equations, and if they make both equations true, then we have a solution. In the first set of equations, if we plug in 4 for x, we'll have 2 times 4, then we'll do plus y, which is 5, and hopefully that equals 13. Well, 2 times 4 is 8, plus 5, that equals 13. 13 equals 13. That is a true statement, so far we're good. Let's try it on the bottom of the equation. So we're going to plug in 4 for x and 5 for y down here. So I'm going to go 4 times x, which is 4 times 4, minus 2 times y, which is 2 times 5, and that should equal 16. If I do the work, 4 times 4 is 16. 2 times 5 is 10. 16 minus 10, that's 6. And that's not equal to 16. These are not true, so we're going to say no. 4, 5 is not a solution to this system. Yes, it worked for one of the equations, but it has to work for both. And the second problem is 0, 4 a solution. Again, we're going to plug in 0 for x and 4 for y into both equations. So I'm going to plug in 0 for that top x, so it's going to be 5 times 0 minus 3 times y, which is 4, and hopefully that equals negative 12. Well, 5 times 0 is 0. Negative 3 times 4 is negative 12. So this is 0 minus 12, which is negative 12. That works. I get negative 12 on both sides of the equation. That's a check. Down at the bottom, I'm going to do negative 2 times x, so negative 2 times 0, plus 2 times y. Y is 4 again. And hopefully that equals 8. Let's see. Negative 2 times 0 is 0, plus 2 times 4 is 8. That checks out. We get 8 on both sides of the equation. Since the point 0, 4 works on both equations, this is a yes. What I'd like you to do is I'd like you to try out this third problem. Substitute 2 and 3 into this equation for x and y. We'll pause the video and we'll see if you get a yes or no for this last equation in just a moment. So here we go. We're going to try 2 and 3 into this equation. We're going to plug in 2 for each x and 3 in for each y. We'll start with the top equation first. We're going to plug in 3 for y, and we're going to plug in 2 for x. So 3 equals 2 times 2 plus 1. Well, we have a 3 on the left side of the equation. On the right side of the equation, I have 2 times 2, which is 4, plus 1 equals 5. Ooh, that is not true. That's a no. And if that equation doesn't work, it doesn't matter if the last one works or not. This is automatically a no. If you wanted to check out the second equation, you could plug in 3 for y again. You could plug in 2 for x. So we have 3 equals 3 times x, or 3 times 2 minus 3. And here, 3 times 2 is 6, minus 3 is 3. So we do have 3 on the right side, 3 on the left side. That equation, it works, but it doesn't matter. We've already shown it doesn't work for the first equation, and to be a solution, it has to work. That solution has to work for both equations. We're going to look at some graphs of systems of equations, and on a graph, a solution to a system of equations is a point, or any point, that exists on both graphs. To solve this first system, we have an equation in slope-intercept form. You may recall that the number before the x is our slope and the number at the end is your y-intercept. So to graph this, while you could do an x and y chart, I would just suggest going 4 units up on the y-axis. There's your y-intercept. And then we're going to do a slope of -2, which means you're going to go down 2 over 1. And if you continue going down 2 and over 1, you'll see the beginnings of what will become a line that goes through these points. So this is my first graph right here that passes through those points we just mentioned. Now our second graph has a y equals 2x minus 2 equation, and again the number in front of the x is your slope. So our slope here is 2, which is the same thing as 2 over 1. And our y-intercept is negative 2. So this graph is going to have a y-intercept of negative 2, and it's going to go up 2 over 1. So we go up 2 over 1, up 2 over 1, and you can kind of see how this graph is going to look like this. There'd be a point down here as well, and here is our graphs. Now a solution to this system is any point that exists on both graphs. Oftentimes what it will be is an intersection point, and you'll see these graphs both appear to intersect right here. It looks like in between 1 and 2, so maybe at 1.5 comma 1. That appears to be the solution to this system of equations. And it actually does work, because if you plug in 1.5 for x in the first equation, you get negative 2 times 1.5, which is negative 3, plus 4, which equals 1. That's your y-coordinate. It also works in the second equation. If you do 2 times 1.5, you get 3, minus 2 equals 1, which is the y-coordinate here. So this equation has one solution, which we find by finding the point that is true on both of these graphs. As we move to the next part of your notes, we're going to have another equation. This time it's written in standard form, and you may recall when we're graphing equations in standard form, I think a smart move to do here is, instead of trying to convert it into slope-intercept form, which can sometimes be a little challenging with the algebra, let's just make a little xy chart. And you may recall in standard form, if you plug in 0 for x, you lose this 3x term. It's 3 times 0, which is 0, so all you have is 2y equals 6. You can divide both sides by 2 and get 3. We'll do the same thing by plugging in 0 for y. If you replace the y with a 0, you have 2 times 0, which goes away. 3x equals 6, so x would have to equal 2. If we graph these points, 0, 3 and 2, 0, what we end up with is a line that goes through these points. It'll do something kind of like this. Now in our second graph, same idea. I'm going to plug in 0 for x, and I'll plug in 0 for y and see what we get for the corresponding coordinates. When you plug in 0 for x, we have negative 4y equals 8. We don't lose the negative sign. It's negative 4y equals 8. 8 divided by negative 4 is negative 2. On the other side, if we plug in 0 for y, we have negative 4 times y, which is 0. So this goes away, and you just have 4x equals 8. So x would equal 2, because 4 times 2 equals 8. So this graph has a point at 0, negative 2. That's your y-intercept. And it also has an x-intercept at 2, 0. And you can see clearly that these lines intersect at the point 2, 0. That is a solution to this system of equations. It's a point that works in both equations. And you'll also notice that it appears on both of our x and y charts. So a solution, again, to a system of equations is an intersection point, any point that both lines contain, or again, it's any point that makes both of these equations true. On our last set of problems, we're going to have equations that are written in both slope-intercept form and standard form. If we have y equals 2x plus 2 and y equals 2x plus 4, the last number of these equations, again, is your y-intercept. So we're going to start by graphing this positive 2. That's your y-intercept. And then we're going to graph your slope, which is the number in front of the x, which is in this case 2, which is like 2 over 1. So from this point, we're going to go up 2 over 1. You get an idea of what the graph is going to look like. And if I continue kind of using this process of vertically 2 over 1, this graph would continue to kind of make its way down this way. And it gives me a few more points to graph. My other line is y equals 2x plus 4. Again, your y-intercept is here at the end. Your slope is here at the beginning, so this graph has a y-intercept of positive 4. It also has a slope of 2, which makes it a little difficult to graph, because if we go up 2 over 1, we're at this point here at 1, 6, which just appears off our graph. But if we continue this process of kind of going down 2 over 1, we're going to continue to see these points, and I feel like I'm close to this other line, but I'm not actually touching it. In fact, I'm never going to touch this other line. These lines are parallel. They're parallel because they have the same slope, which means that these graphs will never share any points in common because they are parallel. There are 0 solutions because if you have graphs that have the same slope, if they're lines with the same slope, and different intercepts, you will never have any solutions. Now, here are lines with different slopes. They are reciprocals of each other, but the fact that they're different means that we will get different solutions here. Y equals 2x plus 1. Again, we're going to go up 1. That's your y-intercept, so we're going to go up 1. Slope is 2. That's like up 2 over 1, so similar to our last problem, we have points that are going to go up 2 over 1. If I work the other way, it's going to go down 2, left 1. And here's my first graph. Y equals 1/2 x minus 2. There's your y-intercept. It's at negative 2. And then your slope is up 1 over 2. So from this point, we're going to go up 1 over 2. And it looks like to the right, we're not going to have any solutions. But as we move our way to the left, if we go down 1 over 2, hey, they have a common point right there. And as I try to sketch these graphs here, these points appear to intersect at the point negative 2 comma negative 3. So the number of solutions is 1, and that solution was at negative 2 comma negative 3. If you have lines with different slopes, you will have one solution. On our graphs at the bottom, again, here we are in standard form, so we make a little XY chart. 2x plus 4y equals 8. If I plug in 0 for x, I have 4y equals 8, so y would have to equal 2. If I plug in 0 for y, 4y, 4 times 0 is 0, so I have 2x equals 8, so x would have to equal 4. This is a line that would have a y-intercept at 0, 2, an x-intercept at 4, 0. And as we connect the points, you're going to get something that looks like this. Kind of goes over 2, up 1, if we continue this pattern. Now my other graph has 4x plus 8y equals 24. So as I'm graphing points here, I'm going to plug in 0 for x. That's going to give me 3 for y, because 8 times 3 is 24. If I plug in 0 for y, I have 4x equals 24, so x would equal 6. Again, I'm a little bit off my graph here, but that's not a big deal. So I have a point at 6, 0, a point at 0, 3. And as I connect these points, I'm going to notice again that these are lines that appear to be parallel to each other. You have this process of going over 2, up 1. So just like we had before, no solutions when our slope is the same, but we have different intercepts. So are there anything possible? Is it basically if they have different slopes, there's 1, and the same slope, it's 0? Well, check out this last case. We have 5x plus 3y equals 15. Again, if I do my little xy chart, if I plug in 0 in for x, I have 3y equals 15. Divide both sides by 3, so y would be 5. If I plug in 0 for y, this is gone. I have 5x equals 15, so I have a point at 3, 0. So I have 0, 5 as my y-intercept, 3, 0 as my x-intercept, and my line looks something like this. A little bit better than that, but it basically uses that format. For 10x plus 6y equals 30, again, I'm going to make my little xy chart because it's in standard form. Plug in 0 for x, I get 6y equals 30. 30 divided by 6 is 5. And if I plug in 0 for y, this goes away. I have 10x equals 30. 30 divided by 10 is 3. When I plot these points, it happens to be the same points I had last time. What does this mean? Well, we said a solution to a system is any point that exists on both graphs. Both of these graphs go through 0, 5. Both of these graphs go through 3, 0. Both of these graphs go through any point that's on this line. If we continue this line, it would actually continue to go through a point at 6, negative 5. So 6, negative 5 would also be a point. In fact, as you continue, there would be many, many points. An infinite number of solutions are possible here. So that's what we say, infinite, I-N-F-I-N-I-T-E. There's an infinite number of solutions if it's the same line. Because if the lines are the same, they share all of those points, and there's an infinite number of points in those lines. So now you've figured out how to work with some systems of equations.